The horizon paradox. When the sun is either rising or setting and appears to be just on the horizon, it is in fact below the horizon. The explanation for this seeming paradox is that light from the sun bends slightly when entering the Earth's atmosphere as shown in figure. So we can see that the light from the sun bends in the figure. So this is the apparent position of the sun where we think the sun is located, but actually the sun is here. Since our perception is based on the idea that light travels in straight lines, we perceive the light to be coming from an apparent position that is an angle delta above the sun's true position. So that's this angle delta. Part A, make the simplifying assumptions that the atmosphere has uniform density and hence uniform index of refraction n, and extends to a height h above the Earth's surface, at which point it abruptly stops. Show that the angle delta is given by arc sine and r over r plus h minus arc sine r over r plus h, where r is 6,378 kilometers, is the radius of the Earth. Okay. So I draw the normal to the surface here. So going from the center of the Earth to the atmosphere. And let's call this angle alpha and the deviation angle delta, so that this total angle becomes alpha plus theta. So that's the angle it makes the incident ray makes with the normal to the surface, alpha plus delta, and the alpha is the angle with which it refracts. So if I use Snell's law at this interface, so we have the light coming from the vacuum, the universe. So the index of refraction is 1 sine alpha plus delta, the angle of incidence with respect to the normal, is equal to the index of refraction of the atmosphere, which we're assuming a uniform material, and the angle of refraction is alpha, so n sine alpha. So what I have just written here is basically Snell's law. So this is Snell's law at the interface between space and the atmosphere. So from this equation, I can read sine of alpha plus delta, the deviation angle, is n times sine alpha. But what is sine alpha? We can see from this right triangle here, sine alpha is r divided by r plus h. So it is then n times. So it is n times r divided by r plus h, where r is the radius of the Earth. So with that, alpha plus delta becomes sine inverse nr over r plus h. Now at the same time we have sine alpha here. Sine alpha is r over r plus h from this right triangle. Sine alpha is r over r plus h. So we can see that angle alpha is arc sine r over r plus h. Therefore, we reach the conclusion this angle delta, the deviation angle, is arc sine or sine inverse nr over r plus h minus the angle alpha, which is arc sine r over r plus h. So this is what we were supposed to show in part A of the problem. Part B, calculate this deviation angle delta using n equals 1.0003 and h equals 20 kilometers. How does this compare to the angular radius of the sun, which is about 1/4 of a degree? In actuality, a light ray from the sun bends gradually, not abruptly, since the density and refractive index of the atmosphere change gradually with altitude. Okay, so we're going to use this equation that we have shown in part A to calculate the deviation angle. So arc sine the index of refraction of the atmosphere is 1.00, let's check 3 zeros, 1.0003 times the radius of the Earth, 6,378 kilometers, 10 to 3, divided by 6,378 plus h, 20 kilometers, times 10 to 3 meters, minus arc sine r over r plus h, which is 6,378 times 10 to 3 meters, 6,378 plus 20 times 10 to 3, that's r plus h. So this gives us a deviation angle of 0.22 degrees. What is the angular radius of the sun? So the angular radius is looking from the Earth. We look at in the direction of the center of the sun and in the direction of the edge of the sun. So we see this angular radius from our point of view, and that is 1/4 of a degree. So we see that this deviation angle we calculate is of the order of the angular radius of the sun, which is roughly 1/4 of a degree, 0.25 degrees. Okay, so in this problem, we looked at the perception that the sun appears at this position, but actually because the light coming from the sun bends when it enters the atmosphere, there seems to be this horizon paradox. There is the position that appears for the sun, but actual position of the sun is with angular deviation delta. So if the angle of incidence with respect to the normal to the surface, this is the interface between the atmosphere and space, is alpha plus delta, such that alpha is the angle of refraction when it enters the atmosphere. So this is the angle the refracted ray makes with the normal to the surface. We can write Snell's law. In space, the index of refraction is 1. 1 sine alpha plus delta is n times sine alpha, where n is the index of refraction in atmosphere, which is approximately 1. In most calculations, we take it to be 1, and we see that it's actually 1.0003. Okay, but here it comes from space and enters the atmosphere, so that difference, which is normally insignificant, is significant for this calculation. Okay, so sine alpha plus delta is n sine alpha, where sine alpha can be read from this right triangle as r over r plus h. So n times r over r plus h is sine alpha plus delta. and sine alpha is r over r plus h from this right triangle. So delta can be written as sine inverse nr over r plus h minus alpha, which is sine inverse r over r plus h. Substituting the numbers, we find that this delta is 0.22 degrees, and if you look at the angular radius of the sun, looking from the earth towards the center and towards the edge of the sun, we see that this angular radius 0.25 degrees is comparable with our angle of deviation 0.22 degrees.